Hello everyone, September the 2nd. Alright, let's get right into it. Unique binary search tree number 2. Unique binary search tree. Given an integer n, return all the structurally unique binary search tree, which has exactly n nodes of unique value from 1 to n. Return the answer in any order. Holy guacamole. We have to return all the binary. I have done something like this in my data structure class. I think we have a requirement, like when we learn binary search tree, we have to return all of them. And I wrote that in C++. No, it's in C++. All right. I mean, what was the idea when we do this? I don't remember. All valid binary search tree. So we're given a list of values, right? I mean, we can say we pick any node. Yeah, any node can be used as a root node. Any node can be used as a root. Now once we pick the root, now we have the remaining, and then the remaining can build their binary search tree, whatever binary search tree they do, or pick a node out of the remaining, right? Or pick a node out of the remaining, and hold on, all the binary search tree that we can do, right? And then what? All the binary search they can do from one root, right? So if I pick, so I'm looking at 1, 2, 3, 4, 5, right? So if I pick 1 as the root, now we have 2, 3, 4, 5. So I can pick 2, which is all the binary search tree that can be made from these, right? And from these, but that will be just a single root, right? A single root. So I pick like 2, and everything can be made from 3, 4, 5. So we say we pick 3, we pick 4, and we pick 5, right? And then from 4, 5, we can do, well, from 4, 5, we can also do the split. Well, can we split? We cannot split. Oh, left and right. Because if we start with 1, everything will be on the right side. Yeah. So whenever we pick a root, then we'll have the left half and the right half. So we make all the binary search on the left half, make all the tree on the right half, and then we stick them together. Yeah, I think we can do it recursion. That shall be it. So we want one root, right? So every recursion will return a tree with one root. And how do we cache this? How do we cache this? Well, we cache it. We probably need to cache it separately, like not using LU cache, but we create a cache, right? Which is just an array, and each position will be all the nodes, all the tree that can be made from that, right? From that. Oh, but it's not the same though. Oh, I just noticed one thing. The constraints is 8. So it's 2 to the nth. 2 to the nth. Yeah, that's what I thought. It has to be, because we have to recompute it, right? Like if you pick 2, right, you say I want all the binary trees with the root as 1. But that's different from all the binary trees already found, because they include 2, but this cannot include 2. Ah, I see. I see. So, yeah, so I think we can, I don't have like a perfect plan, but I feel like we are, I feel like I have something in my mind. Let's give it a shot. So here is what I'm going to do. And we don't need test case for this. All right, so what we need is a gigantic recursion, right? Generate trees. Huh. Do we need a helper? Do we need a helper? Yeah, we do need a helper. We do need a helper. So let's call it def helper. Def helper, we just call the root value, right? So we're gonna get a root. Hold on. What do we get? I'm gonna return a root. So what we give is just a value, yeah, a root value, and we will return an optional, right, or return a list, a tree node, an optional tree node, right? So find the root value, right, and what we can, we also need to know the left and right boundaries, right? We need to know the boundaries. No, it's the boundaries. It's the low and the high. The low and high. That's what we passed in. We have the low and we have the high. So what we need to know is all the trees that can be produced from this, right? And this will return a list, right? Isn't this going to return a list of trees? So what we want to do is setting a low and a high and return all the trees, all the subtrees that can be made from this, and they will have a single root, right? A single root. So we're going to start from the low, right? And then we go towards the high. So what we're going to do is res equals this, right? So we're going to take low. So for bow in range low to high, right? That's our value, and we're going to take the root is going to be a tree node of val, right? Let's say val equals val, so a tree node, and we're going to do helper, right? Low towards val minus 1, right? And a helper val plus 1 to high, right? And we need to do if low is larger than high, then we return none, right? So root is this, so root dot left equals, oh, this will give us, holy guacamole. So there's all the lefts. There's all the left children. Lefts and rights, right? Lefts and rights. So we have a root, and we have all the lefts, we have all the rights. Then we need to product. This is not this will return a list of options of tree node, right? And then we just product them, right? So we can say for left, right in product. Isn't that from import iter_tool? I think that's iter_tools. iter_tools.product, right? Product, we can actually just do this, right? And then helper right. Yeah, I can do left and right, and then we do a product of them, so left and right. Ah, awesome. Rest.append. Ooh, hold on. How do you? Oh, okay. So this has to be this way. So we get this. Then we get root. Then we can say left equals left and right equals right, right? So that is a node, and then we can produce this node and put it in the result. So for this, and for each one, we do a bunch of this, right? And then after we're done, we return res. And we're gonna call return helper 1 to n. All right, let's try this. Let's see if this one works. None type object is not iterable. Huh. Because I return a none, but it has to be a list. Okay, I'll try it again. Yeah, I guess that is. I mean, we can test every single one. Let's test 8. Show diff. Yeah, I think we got it. Do you think we can just say product? I think we can. Yeah, we can. All right, let's submit this. Yeah, submit, pending, accepted. Yep. From iter_tool, import. No, I'll import from import product, right? And then we can just say product. So it looks challenging, right? This problem looks quite challenging, as it requires us to produce all valid BST given an input n. However, it can be solved elegantly with recursion. The idea is that we can pick any value from a given range, right? Then we produce all possible BST. Get any value, let's say v, from a given range, low to high. Then we produce all possible BST from low to v-1, right? And from v+1 to high. After that, we what we say, like mix and match all. So all possibility from as potential left subtrees, right? And from this as potential write subtrees. And after that, we mix and match all the subtrees on the left and the right and add them to the root node specified by v. And then we're done. So the runtime is going to be, we're going to take, let's say at each one, right? So we're going to take one and then the remaining. And the remaining will take this, remaining, take this, take each one. What is the runtime? The runtime is all possible ways to get a range. And I think it's 2 to the n, right? It's 2 to the n. But I don't have a good argument for this, right? Because I say for each value, right? For each value and for the remaining value, we're gonna do. No, we basically just say we're gonna split it into different range. So each range will be computed. So range of 1 will be computed, range of 2 will be computed, range of 3 will be computed. So that means n. All right, so that's that. That's 1. That'll be 1 plus 2 plus 3 all the way plus to n. That's O(n) squared. That's that many. And then, because we have to do that for every single one, we have to do that. I don't know. What's the runtime? Yeah, we're not repeating when we call this function. No, we're not repeating, right? So the ranges, there are n squared ranges, right? So when each time we call it, we have to go through this part. So is that n to the third? I don't think so. I think I've given us only 8. Yeah, that's something I'm trouble with. I'm gonna take a look. Yeah, what is a runtime? Oh my god. Very slow. Are we repeating ourselves? Oh, we are. We are repeating ourselves. I just realized. Yeah, we are repeating ourselves. Let's cache it. Let's cache it. If we cache it, the runtime will be. I still don't know. No, it'll be O(n) squared. If we cache it, it shall be O(n) squared. Ah, how could this pass, right? It should make the time tighter so that if you don't cache, you cannot pass. Oh, but how do you pass? How do you cache? Oh yeah, because the input is 2 values, we can cache. Right? So we can just test a custom case and just run it. Let's see if it works. I forgot. I forgot it here. Alright, I'll run code. Yeah, you can cache. Yeah, you can cache. Let's see if it's faster if we cache it. So with cache, I think with memoization, the time complexity should be O(n) squared, because we visit each range only once, right? Oh, visit each once, but we have the product. We have the product. So that's not O(n) squared. So when you do the product, how do you reconcile the product? Product is, oh my. Is the result times, okay, I don't know. I don't know. I'm troubled by figuring out the time complexity. And then we run this at 85 milliseconds, 11%. All right, let's see. The majority of answers is here. Helper, and this, return this, blah, blah, blah. Yes. Yeah, it's the exact same, but how about the time complexity? Now, this is when we have to be strong. He needs to lose weight, so we have to be strong. Oh, I've done this before. It's number 95. A long time ago. Yeah, cache can make this just slightly faster. All right. Last time I done it, 2020. 2020, July the 6th. Wait, 2020? July the 6th? I think this is part of, I already started doing the daily challenge, right? Let's see the original solution I had. It's probably the same as what I have right now. Oh my dear God, look at this. Oh my, oh, it's painful. Oh, it's painful. What the hell is this? Oh, it's painful to look.
Oh.
Look at this is the current solution. Like what? 10 lines. This is the original solution. Like 60 lines, 50 lines. Oh, it's painful to watch. No, I'm not gonna read it. That's too painful. And I have a better one, probably similar to what I had today. Let's see. Build trees. Yeah, it's the same. But you know what? Maybe this is faster than product. I don't know. Who knows? Doesn't matter. Yeah, this is the right way to go. So what is the time complexity? Hold on. DFS with memoization. That's the time complexity. What the hell is a Catalan number? hash. All right, let's see. This guy says he explained the complexity. I need to see. Oh, what is this? A vote. All right, time complexity 4 to the n, or n times cn. Cn is a Catalan number. Oh, he made a video explaining this. All right, I won't read. I don't want to watch a video. Ha! This is from a guy who's recording a video right now. Why the number of nodes in the BST with n nodes is a Catalan number? Do I need to check out this problem first? Wait, how is this is number 2 and this is number 1? I might have done this one too. Oh, this is the computer total number of. Yeah, I've done this too. 6 and 7. Huh. 2020. Probably no solution. No. Some people explain Catalan number. Here we go. Okay, enumerate each number I and then use the number as the root and choose a sequence left or lay on the yeah. And then construct subtree from the subsequence blah 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 blah. Yep. The problem is to calculate the number of unique. Okay. The number of unique BST for a sequence of length n. And if in is the number of unique, the number I is the root of BST, and the sequence ranges from 1 to n. Dn is the actual function we need to calculate. We derived from which n will also refer to gn. You can see that the total number of unique BST is the sum of fi. There's a y as root, 2 as root, The bottom case, there's only one combination to construct out of a sequence of length 1, only a root, or 0, empty tree. Yes. Okay, so that's the base case. And given a sequence 1 to n, we pick a number I out of the sequence of root, and the number of unique BST is specified. Root fi is the Cartesian product, yes, of the number of BST for its left and right. For example, this, the number of unique BST tree with number 3 as its root. To construct an unique out of the entire sequence. So we have to say if this equals G2, yeah, because 1, 2, and G4. That n is just a total number, right? That's just total number. So f and n is like slightly different. The number of a sequence of length. So if I be I minus 1 and n minus I. Combining the above two will obtain a recursion formula. Gn is, guess we have this plus this plus this. We need to start with low number, so we have these two as a starting point, right? And then depends on the value of G0. So G is this, right? G0, G1 is 1. So we have to compute G2. All right, G2 will be G minus 1 and I minus J is, so I is the total number, J is from 1 towards the end, so J minus 1 to this, and then we multiply them together. So that is, so this is, well, that's actually it's a good one. So this is the Catalan number, right? That's what the Catalan number is. A direct formula for Catalan number. So that Catalan number is, I'm going to read this later today. The total number of binary trees, binary search trees one can find, I like this in the past, can find given a sequence of n, from 1 to n, right, 1 to n. Therefore, when you compute, the complexity is, we have to compute 1 to n, and then 1 to 7. It's not 1 to 7, it's just n. It's just the total, no, it is 1 to 7. Or 1 to 8, right? 1 to 7. What is this question again? Is n nodes. Fn, I think it's the sequence. It's the sequence. Sequence of natural number that occur in various counting problems. Yeah, I think it's the sequence. A sequence of 5 numbers can generate. Yeah, so what we need is a sequence of 1, sequence of 2, sequence of 3, and if we cache it, everyone will compute it once. Yep. Alright, so I like this, and alright, update regarding the time complexity. Refer to this Catalan number is the number of BST, number of unique BST given a sequence of number Cn is the number of a sequence of n values, n numbers. Alright, I just proved that even if I've done it before, I forgot about Catalan number altogether, but we did maintain the ability to do it in the recursion, in the dynamic programming. So that's the plus. I don't remember Catalan number at all. Alright, anyway, that will be it for today. See you guys tomorrow. Adios.